For hundreds of years, a simple magnetic needle floating in a wooden box was all a sailor needed to navigate the globe. But place that same instrument inside a modern cargo ship, and it becomes completely useless. The problem is the ship itself. Modern maritime transport relies on vessels built from tens of thousands of tons of heavy steel. When you put a tiny magnetic compass inside a massive steel hull, you are essentially trapping it inside a giant magnet. As a steel vessel sits within the Earth's magnetic field, the planet naturally forces the metal's internal magnetic domains to align. This creates soft iron magnetism, which constantly shifts as the ship turns. On top of that, the extreme heat of welding and the percussive shocks of hammering during construction bake permanent hard iron magnetism directly into the hull. Together, they drag the compass needle wildly off course. Navigators tried to fight this physics problem with more physics. They surrounded the compass binnacle with a complex array of correctors, using permanent magnets and heavy iron spheres to artificially cancel out the ship's massive magnetic pull. But this intricate web of correctors is incredibly fragile. A change in the type of cargo being hauled, routine structural maintenance, or even just sailing to a different latitude can easily throw the delicate magnetic balance off all over again. To keep global shipping running reliably, the maritime industry had to stop fighting the flaws of magnetic fields. They needed a compass that didn't rely on magnetism at all, forcing them to harness an entirely different law of physics to point them north. The solution came in the form of the mechanical gyroscope. At its core, a gyroscope is a heavy metal disc spinning freely at thousands of revolutions per minute inside a multi-ringed gimbal. As it spins, it builds intense angular momentum, allowing the disc to hold a perfectly steady position relative to the universe, no matter how the ship moves around it. This animation illustrates the immediate geographic problem. Because the spinning disc locks itself to the wider universe, it ignores the planet we are actually on. As the Earth physically rotates over a 24-hour period, the compass appears to drift aimlessly, making it useless for local navigation. To stop this random drift, engineers had to force the spinning disc to lock onto the Earth. They did this by intentionally adding a mechanical weight to the bottom of the gimbal to physically resist or damp its natural movement. Pushing down on the weight introduces the counterintuitive physics of torque, specifically the right-hand rule. When you push down on a fast-spinning disc, the force doesn't make it tip over. Instead, the interaction of angular momentum creates an entirely new rotational force, exactly 90 degrees away from the downward push. This interaction creates gyroscopic precession. Instead of tilting over, the disc sweeps horizontally. Because the Earth is constantly rotating beneath the ship, it is always trying to change the disc's angle relative to the horizon, which keeps the damping weight engaged and the horizontal sweep active. The gyroscope will continue this horizontal sweep until its own spin axis reaches a state of equilibrium. This only happens when the disc is perfectly parallel with the spin axis of the Earth itself. Once the two axes are aligned, the tilting force disappears, the precession stops, and the compass settles permanently on true north. By simply adding a bit of mechanical friction to a spinning piece of metal, engineers force the system into a minimum energy state. They successfully locked the compass onto the rotation of the planet, finding north without a single magnet. The physics of precession work flawlessly if the instrument stays in one spot, but ships are designed to move across oceans, and traveling at 25 knots introduces a new physical variable into the equation. Imagine a cargo ship steaming due north. As it follows the curvature of the Earth's surface, the gyroscope inside, still trying to hold its original alignment with the universe, naturally tilts its bow upward toward the sky. Once again, the mechanical damping weight fights this upward tilt by applying a downward force, and due to precession, that downward force makes the gyrocompass slowly drift toward the mast. Navigators call this physical phenomenon steaming error. Because steaming error is dictated entirely by the strict laws of physics, it is highly predictable. If you know the ship's speed, its current course, and its latitude, you can calculate exactly how far the compass will drift. On modern vessels, the mechanical gyrocompass is wired directly into the ship's GPS feed. The onboard computer uses real-time speed and heading data to continuously calculate and mathematically erase this steaming error before the navigator even reads the dial. While math solved the errors of motion, the mechanical complexity of spinning discs and gimbals still meant dealing with physical friction and wear. To reach a near-zero maintenance profile, engineers looked for a way to navigate without any moving parts at all. The current state-of-the-art is the fiber-optic gyro compass, or FOG. Instead of using mechanical angular momentum, it is a solid-state device governed entirely by the speed of light and the principles of quantum optics. This diagram outlines the internal mechanics. A light source hits a beam splitter, which turns a single pulse of light into two identical halves. These two pulses are sent racing in exact opposite directions, clockwise and counterclockwise, through a massive circular coil of fiber optic wire. If the ship is sitting perfectly still in the water, both light pulses travel the exact same physical distance through the loop and hit the exit detector at the exact same time. But this introduces the Sagnac effect. If the ship rotates even a fraction of a degree, the physical coil rotates with it. Because the speed of light is an absolute constant, the pulse traveling against the direction of the rotation actually has a shorter physical distance to travel, meaning it hits the exit detector first. The system precisely measures this microscopic time delay between the two arriving light pulses. By stacking 3 of these fiber optic coils perfectly perpendicular to each other, the onboard computer can instantly sense the ship's exact physical rotation across all 3 dimensions. By measuring the absolute constant of light against a rotating frame of reference, engineers successfully built a digital compass with 0 moving parts and nearly absolute precision. When you watch a 400-meter container ship carving its way efficiently across the Pacific Ocean, it is easy to take for granted that the crew simply knows which way they are pointing. But the transition from wooden sailboats to tens of thousands of tons of heavy steel forced maritime engineers to abandon the flawed, local frame of reference provided by the Earth's magnetic fields. They stripped the unreliability of wandering poles and induced magnetism out of the equation entirely, by choosing instead to anchor ships to the immutable movement of the planet itself in space. Whether they are utilizing the heavy mechanical torque of a spinning metal disk or measuring the precise quantum shift of light, modern ships navigate strictly by feeling